What happens when gravity breaks its own rules? This shape at the centre of our galaxy should not exist. Gravity creates spheres, always. But look at this. Look at it. A football, crushed, stretched, warped. Like someone grabbed both ends and pulled. This is Sagittarius A star, the supermassive black hole anchoring the Milky Way. And it should not look like this. They told us Sagittarius A star was dormant, a sleeping giant that holds our galaxy together for 50 years. That was the story. The textbooks said it. The documentaries repeated it. Case closed. But new data just proved the giant isn't sleeping. It's sprinting. On January 9th, new analysis confirmed the rotation speed, 90% of the maximum possible angular momentum. If you know your physics, that number is terrifying. It's the theoretical limit, the red line, the point where the fabric of space-time starts to tear. 3 things have converged in the last year. First, the Event Horizon Telescope team published their spin measurement. 90%, 1 notch below catastrophic failure. Second, ALMA data revealed space tornadoes streaming from the core. Violent structures that shouldn't exist around a dormant object. Third, and this dropped yesterday, a paper from Argentina challenges everything. What if it's not a black hole at all? If that paper is right, it explains everything. Dark matter, galactic formation, the center of every galaxy in the universe. Everything. Make sure you're subscribed, because when this breaks, you need to be here. If you've been following this channel, you know I've been tracking 3i Atlas, hunting for tiny anomalies in our solar system that don't fit the official model, geometric patterns, impossible chemistry, the kind of details that get buried in the data. But while we were watching that comet drift past Mars, something else hit maximum RPM. The engine at the centre of our galaxy, the object that controls the motion of 400 billion stars. We track anomalies here, and a supermassive object spinning at 90% of the theoretical limit. That's the ultimate anomaly. It turns out the impossible motion of 3i Atlas is nothing compared to what's happening 26,000 light-years away, at the centre of everything, at the heart of the place we call home. So let's talk about what's really happening at the core of the Milky Way. Because the story you learned in school, it just fell apart. For half a century, we've been told Sagittarius A star is a supermassive black hole, 4 million times the mass of our Sun, sitting at the galactic centre like an anchor, holding everything in orbit, and for the most part it's quiet, dormant, not feeding, not flaring, just sitting there in the dark doing its job. That was the narrative. Scientists called it a quiescent black hole. Astronomers mapped the orbits of stars around it. Everything made sense. The math worked. The observations fit. Sagittarius A star was the textbook example of a supermassive black hole. Stable, predictable, safe. But here's what they didn't tell you. Here's what the data is now screaming. That black hole isn't dormant. It's spinning, and it's spinning so fast that it's warping the space around it into shapes that shouldn't exist. How fast is too fast? What does it mean when the centre of our galaxy is redlining? Let me explain what spin means for a black hole. When something spins, it drags the space around it. You feel this on Earth. It's called frame dragging. But on Earth, the effect is so tiny you'd never notice it. A spinning planet drags space by micrometers, negligible. But a black hole spinning at 90% of maximum, it doesn't drag space-time, it shreds it, tears it, rips it apart. Imagine a ceiling fan. When it's off, the air is still. Turn it on low, you get a breeze, but crank it to maximum speed, and the air doesn't just move, it creates a vortex, a spiral. The blades aren't just pushing air anymore, they're tearing it, ripping it apart. That's what's happening at Sagittarius A star. The black hole is the fan, space-time is the air, and the speed? It's maxed out, redlined. one notch from breaking. In 2024, astronomers published new spin measurements. They used the Event Horizon Telescope, the same instrument that gave us the first image of a black hole in 2019, the same one. They analysed the light, the accretion disk, the magnetic fields, and they calculated the spin. 90% of the physical limit of the universe, that's the number you need to understand. At 100%, the event horizon breaks down. The sphere becomes unstable, it stretches, it warps, it turns into that football shape. 90% means we're at the edge. One more push, and physics shatters. So why is it spinning so fast? Black holes don't just spin for no reason. Something had to accelerate it. There are only two ways: feed it, or merge it with another black hole. But Sagittarius A star isn't feeding. It's been quiet, and there's no evidence of a merger. So we have a paradox. How did it get this fast? What pushed it to the limit? Why is it at 90% when every model says it shouldn't be? It's spinning at the absolute limit of physics, but it hasn't eaten enough matter to spin that fast. It's breaking the rules of black holes. The math doesn't work, the physics doesn't fit, something is wrong. And that's why a team from Argentina just proposed a solution that scares the hell out of the establishment. They think the math doesn't work because it's not a black hole. On February 11th, 2026, a paper was published in monthly notices of the Royal Astronomical Society. The researchers are from the Institute of Astrophysics of La Plata, and their conclusion is stunning. What if Sagittarius A star is something else entirely? A dense core of dark matter. Let me walk you through what that means, because this is where everything flips, where the floor drops out. We know dark matter exists. We can't see it, we can't touch it. But we know it's there because galaxies rotate too fast. Something invisible is holding them together. Dark matter. It makes up 85% of the matter in the universe, and we have no idea what it is. None. The La Plata researchers are proposing that dark matter isn't just floating around galaxies, it's concentrated at the centre, compressed into a core. Think of it like this. Imagine trying to squeeze 1,000 magnets together when they're all repelling each other. They resist. They refuse to collapse. They push back. That's what dark matter particles do. They push back. And if you have 4 million solar masses of this stuff packed tightly together, you get a core. A dense ball. Held up not by pressure, not by heat, but by the fact that the particles simply will not stack on top of each other. They refuse. A ghost ball. This core would have no event horizon, no black hole boundary, no point of no return, just a smooth sphere of invisible mass. And from the outside it would look almost identical to a black hole. Same gravitational pull, same lensing of light, same orbital dynamics, but critically it could spin faster, because there's no event horizon to break down, no limit imposed by the instability of a singularity. A dark matter core could hit 90%, maybe even higher, without the physics falling apart. Now let me show you the evidence that backs this up, because this isn't speculation, this is observation. In March of 2025, the Atacama Large Millimeter Array, ALMA, discovered something they'd never seen before: space tornadoes, long narrow streaks of superheated gas moving at incredible speeds, streaming away from Sagittarius A star. Here's what's happening. The object at the centre is spinning so fast that it's dragging spacetime into a whirlpool, a maelstrom. Imagine a bathtub drain, but the drain itself is spinning, faster than the water can keep up. That creates shear forces, turbulence, chaos. Clouds of gas drift through the galactic core, and then they hit the frame, dragging zone, the region where space-time itself is rotating, spinning, and they get ripped apart, twisted into spirals, tornadic structures that stretch for light years, violent, chaotic, beautiful. You don't get space tornadoes from a sleeping giant. You get them from an engine running at Redline, maxed out. And they've never seen anything like this anywhere else in the galaxy. Nowhere. So the spin is real. Whether it's a black hole or a dark matter core, something is tearing spacetime apart. Now here's the second piece of evidence. A star called S2. S2 is special. It's one of a cluster of stars orbiting extremely close to the black hole. We're talking tight orbits. S2 completes one lap every 16 years. Its closest approach to Sagittarius A star, 120 astronomical units. That's about 4 times the distance from the Sun to Neptune, which sounds far, until you realise it's orbiting a black hole. At that distance, S2 is moving at 5,000 kilometres per second. That's 1.7% the speed of light, screaming, and we've been watching it. For 30 years, we've tracked its orbit with telescopes in Chile, Hawaii, and space. The Very Large Telescope, Keck Observatory, Hubble, watching, measuring, calculating, and the data is stunning. Einstein predicted that a star orbiting a black hole should wobble. The orbit itself should rotate, like a spinning top. And that's exactly what we see. Einstein wins. But here's the problem. The orbit is too perfect. When you measure something in astrophysics, there's always noise, always uncertainty, always small deviations. But S2's orbit, it fits the predictions to within 0.01%. That level of precision is suspicious, not because the data is wrong, but because it raises a question. What is it orbiting? Why is it so perfect? What kind of object creates an orbit with zero turbulence? If the orbit is this perfect, this stable, this predictable, then what is it orbiting? A black hole with those properties should have irregularities, fluctuations, wobbles caused by surrounding matter, nearby stars in falling gas. But S2's orbit is clean, pristine. Like it's orbiting something that has no surface, no accretion disk, no turbulence, just pure gravity, a phantom, something that shouldn't exist. And here's the third piece of evidence, the image. In May of 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A star. You've probably seen it. A blurry orange ring with a dark centre, the shadow of the black hole, the boundary where light can't escape. It was hailed as proof. Visual confirmation that Sagittarius A star is a supermassive black hole. The image matched the simulations. The ring diameter, the brightness, the structure, everything fit. But here's what they didn't emphasize. That same image could be produced by something else. A dense core of matter, compressed to extreme density, warping light just like a black hole. But without an event horizon, without a singularity, without the point of no return. The La Plata team analysed the orbit of S2. They compared 2 models, one with a black hole at the centre, one with a dark matter core, and they found that both models fit the data. The differences in the predicted orbits? Less than 1%. Within current measurement uncertainties, we can't tell them apart, yet. But here's the kicker. Here's what changes everything. If Sagittarius A star is a dark matter core, it solves several problems. Multiple problems we've been wrestling with for decades. It explains the spin. A core can spin faster without breaking. It explains the stability. No accretion disk means no turbulence. It explains the Event Horizon Telescope image. The light bends the same way. It explains the silence. A core doesn't flare like a black hole. And it raises a question that changes everything about cosmology. If the centre of our galaxy is dark matter, how many other galactic centres are also dark matter? Are black holes the exception, not the rule? Have we been wrong about the architecture of every galaxy? Now, I need to be clear. This is one paper, one model. It's not confirmed, not yet. The majority of astrophysicists still believe Sagittarius A star is a black hole. But the fact that this paper passed peer review, the fact that it was published in a top-tier journal, The fact that the data fits, that's significant. It means the question is legitimate, the door is open. And here's how we'll know for sure. We need sharper observations, better eyes. The Very Large Telescope in Chile is upgrading. New instruments are coming online that can track stars even closer to Sagittarius A star. Stars with orbital periods of just a few years. Their orbits will be faster, tighter, more sensitive to the gravitational field. If there's a difference between a black hole and a dark matter core, those stars will reveal it. They'll tell us the truth. We also need better imaging. The Event Horizon Telescope is expanding, adding more dishes, improving resolution. They're looking for photon rings. Delicate loops of light that form when photons orbit the black hole multiple times before escaping. The structure of those rings is different for a black hole versus dark matter core. If they can resolve those rings, we'll have our answer. But until then, we're left with two possibilities. Two radically different futures. One, Sagittarius A star is a supermassive black hole spinning at 90% of the theoretical maximum. An object so extreme, it's tearing space-time into tornadoes. An anchor at the breaking point. Or two, Sagittarius A star is a dense core of dark matter. An object that's been masquerading as a black hole for 50 years. An imposter. An object that rewrites our understanding of galactic centers and dark matter itself. Which is it? We're about to find out. Let's talk about the stakes, because this isn't just an academic question. This is about the engine that holds our galaxy together. 400 billion stars, including our sun, dance to its rhythm. It's the conductor of a cosmic orchestra, and the conductor just started moving too fast. What happens when the conductor loses control? The Milky Way is a spiral galaxy because of the gravitational pull at the centre, the structure, the arms, the rotation. It all depends on that central mass. All of it. Everything. If that mass is a black hole, we understand the rules. Black holes are predictable. We have equations, models, simulations. We know how they feed, how they grow, how they die. The playbook exists. But if it's dark matter, we have no idea what happens next. No playbook, no models, no predictions. Dark matter doesn't emit light, doesn't radiate, doesn't lose energy. A dark matter core could grow indefinitely, or it could collapse into a black hole, or it could remain stable for the lifetime of the universe. We don't know. And that uncertainty is unsettling, terrifying even. Here's another angle. If Sagittarius A star is dark matter, it means the Event Horizon Telescope image, the one we celebrated as proof of a black hole, was misinterpreted. Not wrong. Misinterpreted. The image showed a ring of light around a dark centre. We assumed that dark centre was an event horizon, but it could just as easily be the shadow of a dense core. Same shape, different object. That's a humbling realization. It means our most advanced instruments, our most sophisticated models still can't tell the difference. We're looking at the centre of our galaxy and we're not sure what we're seeing. The heart of our home. And we can't identify it. Now let's bring it back to the spin. Because whether it's a black hole or a dark matter core, that 90% number is the smoking gun. In physics, when something approaches a theoretical limit, it's either at equilibrium or it's about to change state. There's no middle ground. A black hole at 90% spin is stable. Barely. But it's on the edge. One more feeding event, one more merger, and it crosses the threshold. What happens then? What happens when the speed limit breaks? When the engine redlines? When the anchor snaps? If it's a black hole, the event horizon becomes a naked singularity. The point where gravity is infinite is no longer hidden. It's exposed. Naked singularities are forbidden by general relativity. Cosmic censorship hypothesis says they can't exist. But if Sagittarius A star hits 100%, we'd find out. If it's a dark matter core, there's no singularity to expose, but the core itself could become unstable. The fermions could reach a density where they can't support their own weight, and the core collapses into what? A black hole? A neutron star? something else. We don't have the physics to predict it. And here's the terrifying part. We wouldn't know it's happening until the gravitational waves reach us, 26,000 years after the event. If Sagittarius A star collapsed tomorrow, we wouldn't see it until the year 28,026. Think about that. The anchor could already be gone, right now, at this moment, and we wouldn't know. By then, the galaxy might already be restructuring, orbits shifting, stars ejected, new dynamics taking over. But we'd be living in the before, unaware, blind. That's the stakes. So what do we do with this information? Where do we go from here? First, we watch. The data is coming. New telescopes, new instruments, new observations of S2 and the stars around it. We're going to get higher precision measurements of the orbit, and those measurements will either confirm the black hole model or crack it open. Second, we look for other signs. If Sagittarius A star is a dark matter core, there might be other signatures, gravitational lensing patterns, subtle differences in the light curves of orbiting stars, anomalies in the frame dragging. The space tornadoes themselves might carry clues, the way they form, the way they dissipate, the molecules they contain. ALMA is still analysing the data. Third, we ask harder questions. If it's not a black hole, what does that mean for other galaxies? What does it mean for cosmology? The supermassive black hole at the centre of Messier 87, the one we imaged in 2019, is it also dark matter? What about the black holes merging in LIGO's detections? Are some of those dark matter cores colliding? How many of our assumptions are wrong? This isn't just about Sagittarius A star. This is about rewriting the map, the entire map. And fourth, we prepare for the possibility that we've been wrong. That's hard, humbling. Science doesn't like being wrong, but the data doesn't care. The universe doesn't care. If the evidence points toward dark matter, we follow it, even if it upends 50 years of textbooks, even if it means the anchor of our galaxy is stranger than we imagined, even if everything we thought we knew was incomplete. Make sure you're subscribed, because this story is far from over. The next round of observations is coming in the next 12 months. The Event Horizon Telescope is planning another campaign. The Very Large Telescope is tracking new stars. The data will either confirm what we think we know, or it will blow it apart. And when that data drops, you need to be here. In the meantime, I want to hear from you. Do you think Sagittarius A star is a black hole spinning at the edge of physics? Or is it a dark matter core that's been hiding in plain sight? Drop a comment. Let me know what you think. Because this is the kind of mystery that doesn't have an easy answer. And that's what makes it worth watching. Until next time, keep looking up. And keep asking questions. Because the centre of our galaxy just became the biggest question mark in astronomy, approximately